Welcome back, Mathcounts friends. In today's video, I'm going to be starting a new series called Mathcounts Foundations. There are 14 different categories of Mathcounts problems, and today we're going to start by taking a look at logic. So let's jump right in. And I'm just going to go through a series of problems, and we're going to try to solve them together. So buckle up, and hopefully we can learn some things along the way. I would encourage you, as always, to pause the video at the start of each problem and give it a shot on your own. So now would be a great time to pause and try to work this one out. Okay. It says a particular arithmetic sequence has three terms whose average is 2024. Two terms are added to the sequence, one at the beginning and one at the end, so that the new sequence is also an arithmetic sequence. What is the average of the five terms in the new sequence? Okay, so we've got these three terms, 1, 2, 3, and they're arithmetic. It's an arithmetic sequence, so that means you're going to add something. Let's just say k. We're adding k to get to here, and we're adding another k to get to here. And we take the average of these three, and it's 2024. They, of course, like to use the current year in these problems. And it says then we're going to go and we're going to add some new terms in the sequence. One up above and one down below. And it's still going to be an arithmetic sequence, which means it's still plus k to get here and plus k to get from here to here. So one thing that you can tell from all of this is that whenever you have three terms in an arithmetic sequence, you know, you've got some number here, and then you add k to get up to here, and you subtract k to get down to here. The average of those things is going to be this middle number. So if the average is 2024, that means this middle number has to be 2024. And not only that, but if you add another k to this one, it's going to exactly balance out what you get when you subtract k from this one. So this average is still going to be 2024. So the answer is just 2024 here. 2024. All right. Let's go on to the next one. Feel free to pause it here. This one says that using only quarters, dimes, and nickels, what is the least number of coins you can use to make $2.40? Okay. So if you want to use the smallest number of coins, you kind of want to use as many quarters as possible, right? Because quarters are worth the most. So how many quarters can we use to make something that approaches $2.40? Well, 8 quarters would be $2. 9 quarters would be $2.25, right? $2.25. That's 9 quarters. So we want to use all those quarters. And then we've got how much left? We've got 15 cents left, right? So we're going to have to use 1 nickel and 1 dime. We could use 3 nickels, but that would be using an extra coin. We can do it in just 2 coins. So it's 9 plus 1 plus 1, and that gives us 11 coins total. All right. Feel free to pause the video again on this one. This one says, what is the smallest 4-digit positive integer whose digits sum to 22? Okay, if you want to have a small 4-digit positive integer, you want to make each digit as small as possible. Now the first digit cannot be a 0, or it'll be a 3-digit integer. So if we're making it as small as possible, we might want the first digit to be a 1. And of course, the others can be 0, so we could do 1, 0, 0, 0. But these things have to sum up. The digits have to sum up they have to sum to give you 22. So obviously it's not 1,000. That wouldn't be enough. So we've got to add an additional 21. You know, we've only got it summing to 1 right now, so we need another 21 in these 3 digits down here. And you want to put as many of them as you can in the ones place, because each one that you put in the ones place only adds 1 to your number. And if you put it in another place, it's going to add something bigger. So we can start by just putting 9 of them there. That'll get us up to 1,009. But we've still got a long way to go to get to a sum of 22. So let's put another 9 in the tens place. All right. That gets us to here. Now our sum is 19. We still need to add 3 more. So we can add those threes in the hundreds place. That gives us 1399, and that is the smallest one. So that's our answer. All right, this one says you've got a multiplication table shown, and A, B, C, and D are going to be replaced by these numbers, 2, 3, 5, and 7. And each number is going to be used exactly once. And it says, what is the greatest possible value of the sum of the four products? Okay, so we're going to have C and D and A and B. We don't know what those are yet, but we know that we're going to multiply them, and we're going to get all these pairs, right? We're going to get AC here, we're going to get BC here, we're going to get AD here, and we're going to get BD here. And if you've seen any of my videos talking about how multiplication is rectangles, you will notice that each one of these is the area of a rectangle. So this one is the area of a rectangle of height A and width C. And if you put the four together, you get a bigger rectangle, which has width C plus D and height A plus B. So we've got these four numbers, and the sum of these four products is going to be the product of C plus D and A plus B. So we're going to have one pair of them adding up here and the other pair adding up here. And we want this product to be as big as possible. So there are a lot of possibilities. So for example, the smallest pair we could have would be 2 and 3, so that would be 5. If we had a 5, that would be 5 times 12, right? So that would give us a product of 60. That's the most extreme we could have, this being the smallest and this being the biggest. But these all have to sum to be 17, because 2 plus 3 plus 5 plus 7 is 17. So if you think about like a multiplication table, if you have two numbers that add up to a certain thing, you want them to multiply to be as big as possible. You want these two numbers to be as close to each other as possible. So how can we make a sum of these as close to each other as possible? I guess 17 is the total. So is there any way we could have, well, we can't have 8.5 and 8.5. That would be the best, but these are integers. So what about 8 and 9? Can we somehow get 8 and 9 out of this? And the answer is yes. We could have 7 and 2 be C and D. And if we had 7 and 2, we'd have a 9, and then multiplied by 3 and 5, which is an 8, and that would give us 72. You can see that is bigger than what we got with 5 and 12. And there are probably some other possibilities, but having them as close together as possible is going to give us the greatest product. Okay, so 72 is our final answer on this one. Let's move on to the next one. This one says that there are 4 people will each receive 3 of 12 cookies. Some of the cookies are chocolate chip cookies, some are sugar cookies, and the rest, if any, are oatmeal cookies. If there are just enough chocolate chip cookies so that no matter how they are distributed, everyone is guaranteed to receive at least one chocolate chip cookie, what is the most people that can receive a sugar cookie? So first, we got to figure out how many chocolate chip cookies there are. It gives us this hint saying that there's just enough chocolate chip cookies so that no matter how you distribute them, everyone is guaranteed to receive at least one chocolate chip cookie. So if I was trying not to give someone a chocolate chip cookie, right? I had 12 cookies. They were each going to get 3. And I had these 4 friends. They're each going to get 3 cookies. If I was trying not to give a chocolate chip cookie to this person, I might start by doing 3 chocolate chip cookies here, 3 chocolate chip cookies here, 3 chocolate chip cookies here, and I would have given 9 chocolate chip cookies. And if I had 10 chocolate chip cookies, there's nothing I could do. I would have to give my chocolate chip cookie to this guy. So that must be how many chocolate chip cookies there are, because it says there's just enough so that no matter how they're distributed, everyone is guaranteed to receive at least one chocolate chip cookie. So that means we know that for chocolate chip, it would be equal to 10. That's the number of chocolate chip cookies we have. Okay, so there were 12 cookies altogether. 10 of them are chocolate chip. That means the number of sugar cookies is either going to be 0. So let's write it this way. Sugar is either going to be, it's going to be 0, or it's going to be 1, or it's going to be 2. Actually, it says some of them are sugar cookies, right? So it can't be 0. So it's either 1 or 2. And what does it say? It says, what is the most people that can receive a sugar cookie? Okay, the most people that can receive a sugar cookie is 2, because that's the most you can have is 2 sugar cookies. And if you did that, if you had sugar cookies equal to 2 and chocolate chip is 10, then there wouldn't be any oatmeal cookies. All right, so there you go. That 2 is our final answer on this one. Okay, let's take a look at this one. So this one says that the 465 students in Snackwood Public School like pie, cake, and donuts. If 230 students like at most 2 of these snacks, and 285 like at least 2 of these snacks, how many students like exactly 2 of the snacks? Okay, so I guess each student can like 0 or 1 or 2 or 3 of the snacks, right? And I don't know about 0 because it says they like pie, cake, and donuts. I don't know if that means every student likes at least 1, but for now, let's just say there's these 4 possibilities for each student. Each student can like 0, 1, 2, or 3. And it says if 230 students like at most 2 of these snacks. Okay, so let's draw that. Let's draw at most 2 of these snacks. That's all these numbers here. So there are 230 students who fall into one of these 3 categories, let's say. And then it says there are 285 that like at least 2 of these snacks. So at least 2 would mean one of these 2 categories. So there are 285 students there. And if we add these 2 up, the 230 and the 285, what does that give us? 515, I believe. 515 students. Now, if we add these up, we've counted every student, except we've counted these guys twice. And it says how many students like exactly 2 of the snacks. So the ones that we counted twice is the number we're looking for. And so this number will be higher than the number of students. The original number of students, recall, was up here, 465. This number will be higher than 465 because we've double counted these guys here. So we can just subtract these 2 numbers, and that's going to give me 50. That's the number of students that we've double counted. And that is the number of students that like exactly 2 of the snacks. So that is our final answer, 50. Okay, let's move on to the next one. So this one's pretty tricky. This one says how many triangles of any size are in the figure shown. So we need to think about different types of triangles. One thing that's useful for a problem like this, and you'll often see a problem like this, is to think about breaking it down somehow. And one way to break it down is to look at how many of these cells there are in a triangle. So let's look at the case where there's just one cell is a triangle, right? So some of these cells are not triangles. So these 6 cells in the middle are not triangles, but these 12 cells out on the edge, there's 2 on each spike of the star, those are triangles. So we should count those. We've got 12 triangles there. Now, can we combine 2 cells to make a triangle? And the answer is yes. So for example, we could combine these 2 cells to form a triangle, and these 2 all the way around for each of the 6 spikes. So that would give us 6 more triangles. But there's another way that we can combine. Well, let me erase those 2, and there's 6 there. And then there's another way that we can combine 2 cells to form a triangle. If we combine one of these little guys with one of these guys in here, right? So something like this, that would also form a triangle. So we need to add some more triangles in the 2 cell category. So how many of these are there? I guess for each one of these, there's probably 12 of these guys, right? Because for each one of these little triangles that we had up here, there should be one of these. We should be able to add the neighboring quadrilateral in here to make a triangle. So we're going to add 12. And are there any other ways that we can make a triangle by combining two cells? No, there's not, because if you combine these two cells in here, you get sort of a pentagon thing. So now we can move on to 3. Are there any 3 ways to combine 3 shapes to make a triangle? I kind of doubt it. No. What about 4? So what if we combine 4 cells together? Can we make a triangle? So let's see. Yes, we can. So for example, these 4 cells here would form a triangle, and there are 2 others that make this big triangle, so that would give us 3, and then there's 3 more from this other triangle, so that would give us 6 that are shaped like that. Is there any other way we can combine 4 cells to make a triangle? Yeah, there are. So these triangles are all pointing inward. You know, they're kind of like arrows pointing into the center. But there are also some outward pointing triangles. Let me see if I can draw that. If I draw a triangle that goes all the way from up here, all the way down through the middle, and then pokes out like this, that's another way to make a triangle. And there's a twin of that one pointing the other direction, and that together they form a little bit of a diamond. And then there's another diamond shape with another 2 triangles that's over here, and yet another one that's over here. So altogether I've got, let's see, 3 of those diamonds each have 2 triangles like this, so that's going to give me another 6. And then can I combine even more cells together to make a triangle? Even more than 4. And the answer is yes. I could combine. I got these big triangles, right? I got these big giant triangles here. How many of those are there? There's only 2 of those. How many cells are in that? 1, 2, 3, 4. Well, there's the 6 in the middle, and then there's 6 on the outside, so that's 12 cells. That gives me 2 triangles. Are there any other triangles that we haven't covered yet? I don't think so. So this gives us a total, let's see, 12 plus another 12 plus another 12. That'll be 36, and then another 8. That should be 44. Did I do that right? Let's see. Oh, you know what? That's 44, but I think I did miss some other triangles. Yeah, we could take these giant triangles and we could cut them in half, right? So we could cut this triangle in half this way. Yeah, it looks kind of like the Harry Potter symbol, right? We got the what is that called? The Deathly Hallows here. Yeah, so we could cut it in half this way. We can cut this triangle also in half this way, and we can also cut it in half this way. So for each of these big triangles, we can cut it in half 3 different ways. And every time we cut it in half, we get 2 triangles out of it. So just from this big triangle, we have 6 more. So we have to add another 6. And I guess I should put those in a category. 1, 2, 3, 4, 5, 6. Those are combining, yeah, these are combining 6 cells. There are 6 of those from this triangle, and then from the other triangle there will be another 6. So this is another 12 on top of my 44. That gives me 56. I believe that is the correct answer. Okay, let's take a look at the next one. This one says the product of 6 integers is 1, and their sum is s. What is the product of all possible values of s? Okay, so the most obvious way to get the product of 6 integers to be 1 is to have all the integers be 1, right? 1, 1, 1, 1, 1, and 1. The product of all those integers is, we multiply them all together, the product is going to be 1, and the sum is going to be 6. Is there any other way to get 6 integers to be multiplying to give you 1? And the only other way is to have some negative ones. Because if you put any number bigger than 1, the absolute value is going to go above 1 unless you have a 0 in there, in which case it's going to go to 0. So we can't have anything other than, all these have to be absolute value of 1. They have to either be positive or negative 1. And if we just make one of them negative, when we do the product, we're going to get negative 1. So that doesn't work. If we make two of them negative, that will give us a product of 1. So what's the sum of these? So we'll have two of these negatives will cancel with two of these positive, and we'll just have 2 left. So we can have a sum of 2. And then we can add 2 more negatives, right? Because we don't want to make a negative number, so we have to have an even number of negatives. Now our sum is going to be negative 2. And we can go further. We can make all of them negative 1. These will still multiply to give us 1, but the sum will now be negative 6. Okay, so I think those are all 4 possibilities for what the sum can be. And they want to know what is the product of all possible values of s. That s is the sum. So these are the possible values of s. We need to find the product of those. So let's see, 6 times negative 6 will be 36. And then 2 times negative 2 will be 4. So we have 36 times 4, which gives us 144. So that is our final answer on this one. Okay, they're getting harder as we go. Okay, this one says, how many pairs of numbers A, B satisfy rules 1 and 2 shown here? Okay, there are probably lots of ways to do this, but I want to show you my favorite way. Rule 1 says A is equal to 0, or B is equal to negative 1, or B is equal to 1. So what I was thinking is we could make kind of like an axis of A, like kind of map out the A, what is it called, the AB space, right? So instead of an XY graph, I'm going to make an AB graph, okay? So this is my A axis. Let me make that a little darker. And then I'll have a B axis here, right? So just to make that clear, we'll say this is A and this is B. Okay, so A equals 0 would be what? Well, A equals 0 would be the line going through A equals 0, right? So it would be a vertical line right here on the B axis here. So if we were on that line, and it goes up and down forever, but I'm just going to draw this part of it, then we would satisfy rule number 1. Or we could satisfy rule number 1 by being on the line B equals negative 1, which would be, let's say, this line here. Or we could have B equals positive 1, which would be, let's say, this line here. And again, these lines are going off forever in either direction. So we have these 3 lines, and any point AB that falls on one of these 3 lines is going to satisfy rule 1, right? So this is rule 1. Let's grab a different color for rule 2. So this is going to be rule 2. In order to satisfy rule number 2, we have to be on A equals negative 1, which is this line here. Or we have to be on A equals positive 1, which is this line here. Or we have to be on B equals 0, which is this line here. Okay, so now we have to find a point that is on, basically that satisfies, we have to find we have to find how many pairs of points will satisfy both rule 1 and rule 2. So what does that mean? Well, it means those points have to be somewhere on the pink lines and somewhere on the blue lines at the same time. So we need to look for intersection points between pink and blue lines. So there's one intersection here, which is at 1, 1, right? This is 1, 1. That's one possibility. There's another one here. This is at 1, negative 1. there's another one here, which is at, whoops, I did that wrong. Let me fix that. This was negative 1, 1. Sorry about that. This is negative 1, 1. This one is the one that is 1, negative 1. And then there's also negative 1, negative 1, right? Negative 1, negative 1. And then there's one more, which is right here at the middle, 0, 0. And if you pick any one of these 5 points, you can just compare it to these rules, right? Let's say 0, 0. Is A equal 0 or B equal negative 1 or B equal 1? Yeah, A is equal to 0. And then does it satisfy rule 2? Yeah, because B equals 0. So this point satisfies both rules. And you can do the same thing with all 5 of these, and you'll find that they do work because they're at the intersection of the pink and the blue. And so there are 5 of those pairs. Okay. Just a few more to go here. I know they're getting a little tricky. This one is interesting. This one says if 2 distinct ellipses and a square are drawn, what is the maximum possible number of points at which at least 2 of the 3 planar figures intersect? Okay, I'm going to start with a square because that can be fixed and then we can move the ellipses around it. I mean, there's only one. Every square is similar to every other square. So if I just draw a square, whoops. Ah, yes, I remember now. These squares do not come out as frames. They come out as solid figures. I'll have to figure out how to figure out if there's a way to make a frame. But anyway, I'll just do it this way for now. So we'll draw a square like this. And yeah, every square is similar to every other square. So we can just assume that this is our square and we'll figure out where our ellipses have to be. So the first question is, how many intersections can I have between one ellipse and one square? So let's grab ourselves an ellipse here. And I want to make it so that it intersects as many times as possible. That's kind of hard to think about. I mean, maybe I could intersect, whoops. Maybe I could, how many times can I intersect? Maybe I could do like this. And I get 1, 2, 3, 4, 5, 6. That's a lot of intersections. Is that the best I can do? Well, one thing to think about is that this square is made up of 4 line segments, and each line segment is part of a line. And so you can think about, like, if you had an ellipse, what's the maximum number of intersections between an ellipse and a line? And hopefully you can just kind of visually see that the maximum number of intersections is going to be 2. And so if I can get my ellipse to intersect the top edge of the square twice, and each side twice, and the bottom twice, then that'll be the most intersections that I can get between the ellipse and the square. And so I could do that just by making this ellipse something like this, right? And but I've got to have 2 ellipses, so let's draw another ellipse here. I guess my other ellipse could also intersect 8 times, right? Something like this, for example. That gives me another 8 intersections, but the problem is that now the 2 ellipses don't intersect with each other, and I would kind of like to have those intersection points to give me even more. So let's think about what is the maximum number of times 2 ellipses can intersect each other. And hopefully it's you can kind of just logically reason that out and realize that the most you can do is have 4 intersections between 2 ellipses. So, and that's kind of easy to do if you make one of them fatter and one of them taller. So let's try to do that. Let's go back and let's make our first ellipse a little taller, let's say. So we'll do it something like, oh, I'm going to have to make it fatter than that, though. Let's start again. So, yeah, that's pretty good. Almost made it too big, but we've got 2 intersections here, 2 here, 2 here, and 2 here. Maybe I did make it too big. Let me fix that a little bit. Let's see. Okay, that looks good to me. So now I've got 8 intersections between the square and the ellipse. And now if I go and grab myself a color to do another ellipse, I can, oops, that's not an ellipse. Here we go. I can hopefully make it, yeah, so something like that. And you can see that near each of these corners, I've got a bunch of intersections, right? I've got 2 here, and 2 here, and 1 here. So I've got five intersections right here. And I've got, I didn't draw this one as well, but there's 2 here, 2 here. I guess there's 1 out here in this case. But there's still 5 intersection points. And the same thing here. I've got this 1, 2, 3, 4, 5 intersection points here. And I've got 1, 2, 3, 4, 5 intersection points here. So altogether I've got 20. And that's the most you can do because we decided that the most you could do between an ellipse and a square was 8. And we've got 2 of those. And then between an ellipse and an ellipse is 4. So we've got 2 of these is 16 plus 4 is 20. So 20 is our maximum. So that is our answer. Okay, let's take a look at this one. This one's a classic logic problem here because it's using actual logic gates here. If you haven't seen logic gates, it explains what it is here. So it says the function machine shown here consists of 3 logic functions. So there's these 3 logic functions. This one here, this one here, and this one here. And 2 of them are AND functions, and 1 of them is an OR. So they're going to explain what that means. A Boolean is a member of the set 0, 1. So basically, a Boolean is either a 0 or a 1. For each function, the inputs are on the left and the output is on the right. Okay, so for this AND, you have 2 inputs here, and then you have an output coming out. And then that output is going in as an input to this one. The output of each function is a Boolean. The input of each function is a pair of Booleans. Okay, so we've got 2 Booleans going in and 1 Boolean coming out. For the AND function, the output is 1 if and only if both inputs are 1. So that's why they call it AND, because you have to have this one be a 1 and this one be a 1 in order for this one to be a 1. And then for the OR function, the output is 0 if and only if both inputs are 0. So you have to have a 0 and a 0 in order to get a 0 out here, because if this one is a 1, then one of them is a 1, so it'll spit out 1. And if this one is a 1, also one of them is a 1, so it'll spit out 1. And if both of them are 1, at least one of them is a 1, so it'll spit out 1. So this is just saying, is either one a 1? And this one is saying, are they both a 1? So now it comes to the question. It says, among the 16 distinct sets of inputs. Okay, what does it mean by the 16 distinct sets of inputs? So there are 4 inputs. So for example, one way you could have the inputs is you could have 0, 0, 0, 0. That's one set of inputs that you could have, right? Or you could do 0, 0, 0, 1, or 0, 0, 1, 0. And what you'll hopefully realize quickly is that these are all the binary numbers from 0 up to 15, right? So if we list these all out, the last one will be 1, 1, 1, 1, which in this one is the binary representation of 0. This is the binary representation of 1 and 2, and all the way up to 15. So you've got 16 possible sets of inputs. It says among the 16 sets, these things here, how that can be applied on the far left, how many produce a 1 as the final output on the far right? Okay, so we want a 1 out here. That means we need to have a 1 here and a 1 here. And if you have a 1 here, that means you have to have a 1 here and a 1 here. But you have some more choices here. So with input 3 and 4, you could have a 0 and a 1, or you could have a 1 and a 0. Or, whoops, that's not a 0. 1 and a 0, or you could have a 1 and a 1. Any of these 3 possibilities would give you a 1 on the output. If you had a 0 and a 0, that wouldn't. That would give you a 0 on the output. So we're not counting that one. We're only counting these 3. So basically, these are fixed. They have to be 1 and 1. So you know you've got 1 and 1. And then for the other 2, you could either have 1, 1, or you could have 1, 0, or you could have 0, 1. So basically, these are the 3 sets that will give you a 1 on the output. So that is our answer. Our final answer is 3. Okay, let's take a look at this one. This one says several students were trying out for a class play. When asked which roles they were willing to play, 12 of them were willing to play. So 12 of them were willing to play the knight, 15 were willing to play the princess, and 6 were willing to play the sorcerer. Of these students, 8 were willing to play either the knight or the princess, 5 were willing to play the knight or the sorcerer. This is getting complicated. And 4 were willing to play the princess or the sorcerer. And there's exactly 3 of the students that were willing to play any of the roles. Now the question is, how many students were willing to play the sorcerer but no other role? So this is a lot of information that they've given us. And the way to do a problem like this is to use a Venn diagram. I happen to have one handy right here. So let's take a look. So it said the knight, there were 12. So that means there are 12 students inside this sort of magenta or pink circle. And 15 were willing to play the princess, so that means there are 15 that are in this blue circle. And 6 were willing to play the sorcerer. Okay, so that means there's 6 somewhere in this green circle. And then it tells us that of these students, 8 were willing to play either the knight or the princess. So either the knight or the princess, that is this region here. It's got these two areas together, this sort of football-shaped region here. Both of these regions. Those two together are 8, because 8 was the knight or the princess. I'll put an 8 here. And then maybe I'll do it. It's going to give us these other ones too for this sort of football shape here. And it also gives us a number for this sort of football shape here. So I'm going to give those numbers out kind of at the corners of the football. So there's 8 in this overlap region. That's this whole region here. And then there are, how many? 5 willing to play the knight or the sorcerer. That's here. So that's 5 that are somewhere in this region. And then there are 4 willing to play the princess or the sorcerer. So there's 4 in this region here. Okay, all right, great. All right, now it says exactly 3 of the students were willing to play any of the roles. Okay, that's really useful. So let me get another color here. Let's put that in red right in the middle. There are 3 in this very center spot. So now, given that we have 5 total and 3 of them are in here, that means there's 2 here. And 8 total in here, and 3 in here, that means there's 5 here, and 4, that means there's 1 here. That red doesn't show up very well, does it? Let's see. Maybe I need to erase some of my yellow shading. Let's yeah, I guess let's do that. Oops. Okay, let's see if I can do that here. So that one actually looked pretty good. I probably didn't need to erase that, but I'll just make a little hole in the middle so I can draw these numbers and make it visible. Okay. All right. Okay, so what did we have? We had 3 in the middle. And since there's 8 here, there's 5, there's 2, and there's 1. Okay. And the question is, they want to know how many are out here. They want to know how many are that are willing to play the sorcerer, but no other role. Okay, so there were 6 total that were willing to play the sorcerer, and we've already got 6 here because we've got 2 and 3 and 1. So that means there's nobody left. This is going to be a 0. So 0 is our final answer, and I will put a square around it instead of a circle. Okay, let's take a look at the last 2 problems. These ones are really hard. So I hope you will enjoy these. This one says a set S contains some but not all of the positive integers from 3 to 7. Okay, so 3, 4, 5, 6, 7. We've got some of them but not all of them. Some statements describing S are given below. The statement numbered n is true if the number n is in S and false if n is not in S. Okay, so we need to figure out which of these statements are true, because it asks us what is the product of the numbers that are in S. Okay, so we need to figure out which of these statements are true and which of these statements are false. And this is a tough logic problem here. One way to start attacking a problem like this is just to start thinking about, is there any two that can't be true at the same time? Like, is there any contradictions? So, for example, the sum of the numbers in S is odd. Does that contradict any of these others? So the sum of the numbers is less than 15. That doesn't seem to contradict that. S contains exactly one composite number. Okay, so which ones are the composite numbers? I guess the composite numbers are 4 and 6. The others are going to be prime. So saying that it contains exactly one composite number would mean that either 4 or 6 is true. So if 5 is true, then either 4 or 6 is true. And 6 says S contains exactly one prime number. Okay, so if 6 is true, then we have only one of these odd numbers, or the prime numbers are the same as the odd numbers here. And then number 7 says the product of the numbers in S is odd. Okay, so if the product is odd, is that one possible? The product of the numbers is odd. That means I would have to have only odd numbers. So I would have to pick, I wouldn't be able to have 4 or 6. I would only have these. So I think, let's see, it seems like the product of the numbers is odd. I don't think that can be true at the same time as 5. So I'm looking at these two, 7 and 5. Are those contradictory? S contains exactly one composite number. Yeah, because if it has a composite number, that's going to be even, and the product is going to be even, right? So 5 and 7 can't both be true. We've got to pick one or the other. So you could have 5 and 7. That's not possible. So you could just have 5, or you could have 7, or you could have neither one, right? But you can't have both. All right, that's something. Another thing that's kind of related to this one is this one here, number 3, because it says the sum of the numbers in S is odd. So if that was true, let's just assume that 3 is true for a minute and see what happens. So if 3 is true, what does that mean? So if 3 is true, the sum of the numbers in S is odd. That would mean that I would have to have, I guess, an odd number of these odd numbers. Okay, and so that would mean that it has to be this one or this one. Well, no, because if 3 is true, that's another odd number, right? So if 3 is true and we had 5 but not 7, that would be an even number of odd numbers. And if 3 was true and we had 7 but not 5, that would be an even number of odd numbers. So the only way for 3 to be true is for 5 and 7 to both be false. Okay, so that's one possibility, is that you have 3 the only odd. Only odd. What if 3 is false? So let's go back here. Let's say if 3 is false. If 3 is false, the sum of the numbers in S has to be even in that case. So that would mean that either 5 and 7 are both true, which we know is not possible, or that neither one of them is true. So if 3 is false, we can't have just 5 or just 7. We'd have to have neither one be true. So that would mean there would be no odd numbers. So is that another possibility? 3 is the only odd, or there's no odd numbers. No odd numbers. So let's see, which ones of these are possible? Are either of these possible? 3 is the only odd, or no odd number. Let's say you had no odd numbers. What would that mean? That would mean the sum of the numbers in S is even, yeah. S contains exactly one composite number. Okay, so it would have to be either 4 or 6. Oh no, wait, but we're saying 5 is, we're saying there's no odd numbers, which means it doesn't contain exactly one composite number. So it's got to, so in this case, it would have to be either 4 and 6 or neither. Not one or the other. And then the product of the numbers in S is odd. So that's false. That means the product is even. Yeah. So that could happen. All right. Let's see. So maybe we just have, so in this case, so let's consider these two possibilities. Either you have both 4 and 6 or neither 4 and 6. So if it's neither, then they're all false. And it says it can't all be false because it says the set contains some but not all. So this is not a possibility. So could we have no odd numbers and just either the 4 alone or the 6 alone? So let's take those two possibilities. Let's say 4 is our only one in the set. The sum of the numbers in S is odd. That's false. The sum of the numbers in S is less than 15. That's true. Okay, 4 is true. That's good. S contains exactly one composite number. That's also true. S contains exactly one prime number. That's false. Oh wait, 5 was true, so that doesn't work. Okay, so we can't have 4 be the only number. Can we have 6 be the only number? That's true. So that if we had just 6 in the set, the sum of the numbers of the set is odd. That's false. The sum of the numbers is less than 15. Oh wait, that's true. Oh, with this one also was true. So, oh, but that was because this was number 4. But yeah, if it's only 6, then the sum is less than 15. That makes 4 true, which we already know can't happen. Because now I can't remember why that. Oh, yeah, no. I'm sorry. It was either neither or both. We shouldn't have been looking at the case where there was one or the other. So my bad. Okay. So let's consider the case that they're both true. 4 and 6 are both true. So the sum of the numbers is odd. That's false. The sum of the numbers is less than 15. That's true. S contains exactly one composite number. That's false. S contains exactly one prime number. Oh, wait. That's false. Right? So this can't be. That means this can't be. And now we have 3 is the only odd number, and we just have to figure out what even numbers there can be. All right, I'm going to make some space. This is really a crazy problem. All right, so 3 is the only odd number. I think we've concluded that has to be the case. 3 is the only odd number. And now we just need to figure out the evens, so let's do that. Maybe we'll grab another color for fun. All right, so 3 is true. That means the sum of the numbers is odd. Okay, that makes sense because there's only one odd number. And then the evens, one says the sum of the numbers in S is less than 15. Well, even if we put both 4 and 6 in there, where we have 3 and 4 and 6, it's going to be less than 15. So that means 4 is true. So 3 is true, 4 is also true. We just need to decide about 6. So S contains exactly one composite number. That has to be false. That means we can't have 4 and 6 in there. Or no, wait, if it's false, no, I got that backwards. S contains exactly one composite number is false. That means we're going to have both of them in there. And then 6 says S contains exactly one prime number. That is true. And the product of the numbers is odd. That is false because we've got some even numbers here. So we just need to multiply these 3 numbers together to get our answer. This is 12 times 6, which is 72. Okay. We've got one more problem to go, and it's a tricky one. All right. Let's take a look at this one. This says Edna enters a room with 1,000 bottles lined up in a row left to right. Okay, so you've got 1,000 bottles. 1, 2, 3. I'm not going to draw them all, but we've got a bunch of bottles here. They're all lined up from left to right. Number 1, number 2, number 3, number 4, dot, 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 all the way up to number 1,000. Okay. And one bottle contains a tasteless magic potion. Okay, so we've got some magic potion somewhere in there. We don't know where it is. And it's tasteless. All bottles to the right of the magic potion. Okay, so let's just put the magic potion somewhere. Let's say this is our magic potion bottle. At number, I don't know, X. This is our magic potion bottle here. Maybe we'll put a little stopper on it. Whoops. Okay, that's our magic potion. All the bottles to the right of the magic potion, it says, contain a bitter poison. Okay, so there's poison. This is poison. This next one is poison. This next one is poison. All the way up to the last one is poison. And then it says Edna can drink, and it's bitter, so you can taste this poison. Edna can drink from no more than 2 bottles containing poison before becoming sick and being unable to drink anything else. She can take an unlimited number of drinks from any other bottle. What is the minimum number of bottles from which Edna may need to drink to ensure that she can identify the bottle containing the magic potion no matter where it is in the lineup? Okay. This is a hard one. Now, the worst strategy, I guess, well, the worst strategy is to just start drinking poison, but the worst sort of smart strategy is to start on the left side and to drink number 1. It's probably going to be tasteless, right? Actually, it's guaranteed to be tasteless because even if the magic potion is there, the magic potion is tasteless. So it's going to be tasteless, and then this one will be probably be tasteless, but she can just keep drinking from these bottles until she tastes something bitter. And when she tastes something bitter, that means she's at this one here, which will be X plus 1. So she will start at 1, then she will do 2, then she will do 3, and once she gets up to X plus 1, where X is the magic potion, when she gets to X plus 1, it will suddenly be bitter. And then she will know that X is where the magic potion is, right? So that's one strategy. It's not a very good strategy because she might have to go all the way up to 9.99. Once she got up to 9.99, and if it was bitter, she would know it was 9.98. If it was tasteless, she would know that was the magic potion because, well, no, I guess she would still have to taste 1,000, right? Because 1,000 could be the magic potion too. So she would have to take. In the worst case, she would have to taste 1,000 bottles in order to know which one was the magic potion. With this strategy of just going one by one. So what's a better strategy? You might think. Well, she could just start drinking the odd ones, right? So what would happen if she did that? So we got one case where it took 1,000. So if she just did the odd ones, she would do number 1, and then number 3, and then number 5, and then number 7, and at some point she would taste a bitter one, right? When she tastes that bitter one, she doesn't know if it's bitter minus 1 is the magic potion or bitter minus 2. That's the magic potion because she tasted bitter minus 2, but it was tasteless. It could either be the magic potion or the tasteless water. So she would have to taste one more. She would have to go and taste bitter minus 1. After she tastes the bitter poison here, she would go and she would taste this one, and she would get sick, but she would still know the answer, right? So the poison doesn't kill her; it just makes her sick. and she has to drink 2 of them before it makes her so sick that she can't drink anything else. So this would work. She could do every other one. She tastes B, it's bitter. Then she would go and taste B minus 1. If it's bitter, she knows that the magic potion is in B minus 2. If it's not bitter, then she knows that that's the magic potion. So that's another way she could do it. And then you might think, oh, well, maybe she can skip more than 1. Maybe she could do every third or every fourth or every fifth. And that will help her get up to the bitter one a lot faster, right? So let's say, for example, she skips 10 every time, right? So what would happen in that case? So let's say instead of going by the odds, let's say that she now decides, she's going to skip 10 every time. So she starts at 1, then she goes to 11, then she goes to 21, then she goes to 31 and 41, and at some point she gets bitter. And what does she do once she tastes this bitter one? Like let's just give an example. Let's say the 51 was the bitter one. Well, what does she know? She knows that the magic potion has to be somewhere between 41 and 50. 41 and 50. So she can go back and just start tasting these one at a time. If she skips any, when she goes back here to 41, if she skips any, she'll be in trouble, because then she might end up needing to taste 3 bitter potions to figure out the answer. So she can't skip any once she goes back. So she would go back and she would sample 41, 42, 43, and in the worst case, she would have to taste all the way up to 50, because once she tastes 49, if it's bitter, then she knows the magic potion's at 48. But if 49 is tasteless, it could be the magic potion, or 50 could be the magic potion. So she's got to taste all 10 of these. So she's going to have to taste 10 of these. And now what we're starting to see is a little pattern where the number of things she has to taste in order to get up to the bitter one is going to be whatever the bitter one is divided by 10, or divided by this. Let's call it the stride. Let's say this one's got a stride of 10 because you skip 10, skip ahead 10. So we'll call that the stride. So she can pick whatever stride she wants. In this case, she's doing 10, and in order to get up to the bitter one, she's going to have to do bitter. Let's call the number of steps to get up to there will be bitter divided by stride. And then, so that's the first number of steps, but then she's also going to have to do stride steps plus stride. So this is going to be the total number of steps she's going to have to do. So how do we make this as small as possible? If we make stride big, that will help with this one, but it'll hurt over here, right? And if you think about it a little bit, you'll realize that using a stride of square root of 1,000 might be a good idea, because that will make, because in the worst case where the bitter is up at 1,000, these two terms will be equal to each other. You'll have bitter divided by the square root of 1,000, or you'll have 1,000 divided by the square root of 1,000 plus the square root of 1,000. Now, a square root of 1,000 can't be a stride because it's not an integer, but we would find some value close to, like a little bit bigger maybe than the square root of 1,000. And so this would give you roughly the square root of 1,000 plus square root of 1,000. So it would be like 2 square root of 1,000 would be the best you can do by using a fixed stride like this. But that's not the absolute best you can do, because what you'll notice is that this first stride, it could actually be a lot bigger, because the first stride, if you get a bitter after the first jump, you've only spent one jump. So you can go back and do more than 10, or whatever your optimal stride is. Square root of 1,000. What is square root of 1,000? I don't know, but um, I guess it's going to be 30 something, right? So say you're jumping 30 something, and if you get to the bitter on that first jump, you've got a lot of bottles you can still taste. So, and then with the next jump, you're going to have used one extra jump, so you have one fewer bottle that you can taste to get up to the maximum. So probably the best thing to do is to start with a stride of, the original stride OS, and then the next stride should be the original stride minus 1. And then the next jump should be original stride minus 2. Okay, I'm making a mess here. Let's clean this up a little bit. But now we're getting really close to the answer here. Basically, this is a good strategy of what she should do to minimize the number of bottles that she has to taste. So what she's going to do is she's going to go let's call the original stride n. So she's going to jump n. So it'll be 1, and then it'll go up to 1 plus n, right? And then the next jump will be 1 less than that. It'll be, so instead of jumping n, she'll jump n minus 1, right? So this will go up to, what, 2n, I guess. And then she'll jump n minus 2. This will get her to 3n minus 2, and so on, right? All the way up to, up to somewhere around 1,000, right? In the worst case, where she has to do the most jumps. So what will that be? We want some, we don't want to have to take so many jumps that this value becomes less than 1, right? Our last jump maybe could be 1, but it can't be 0 or something like that. So we need some number n that when you do 1 plus 2 plus 3 plus 4 plus all the way up to plus n, it's got to be at least 1,000, right? So this has got to be bigger than 1,000. Okay, so this is a triangle number, and we have an equation for these triangle numbers. Basically, if you want to find the sum of all these numbers, you've got to have, well, what is that sum going to be? So, let's see. So if you have 1 plus 2 plus 3 all the way up to n, you can pair these up, right? You can say 1 plus n, and then 2 plus n minus 1 is also going to be 1 plus n. So you have n plus 1 multiple times. You have, for each pair of these numbers, you have another n plus 1. So how many pairs of numbers are there? Well, there's n over 2. So this thing has got to be greater than 1,000. Okay, so if I multiply both sides by 2, I get n squared plus n. Well, maybe I won't even do it that way. I'll just say n plus 1 times n. I think that's easier. N plus 1. Oops, n plus 1 times n has got to be greater than 2,000. So n has got to be somewhere around like the square root of 2,000. So what's the square root of 2,000? Square root of 2,000 is going to be like 10 times the square root of 20. Square root of 20 is somewhere between 4 and 5. So this value of n is going to be somewhere between like 40 and 50, let's say. And it's about in the middle because, 4.5 squared is, what is that? Let's see, what's 45? Well, let's try 44 times 45. So if we do 44, so in that case, n is 44, and we'll have n plus 1 be 45. So let's do this out. We get 20, carry the 2, we get 22. Now we get 16, carry the 1, and we get 17. I'm running out of room there, but we get 1980. So that's actually a little bit too low. So we need to go up to n being 45. Here n was 44. So let's say n is 45. Now let's think about this. So we're going to take a leap of 45 in the first bottle. And let's see how that works. I think we're getting close, but let's reason through it. let's say n is 45. So we're going to start by taking a leap of 45, then 44, then 43, and so on. Well, let's see, what's the worst thing that can happen if you do that? So let's go ahead and grab, I don't know, a yellow. So we'll start at 1, then we'll take a leap of 45. That'll get us to 46. And then we'll take a leap of 44. And then we'll take a leap of 43. And if we do all these leaps, what'll that get us up to? We go all the way up, we do all the way up till our last leap is 1. Then we'll be at, this last number that we're at will be 1 plus 40. What will it be? 1 plus 45 plus 1 times 40. What is this? 1 plus 45 times 45 over 2. Okay. So this is 46 over 2, so this will be 1 plus 23 times 45. This is a times. So what's 45 times 23? That's going to be 5. Carry the 1, 3, 1, 0, 1, 9. Whoops, did I do this wrong? Let's see, 135, 90. That's right. So it's 1,035. So yeah, so that'll definitely get us past 1,000. If we do all these jumps, it'll actually get us to 1 plus this. It'll get us to 1036. So that'll get us as far as we need to go. I think we figured out if we use 44, it wouldn't get us far enough. So this strategy is gonna work to get us up to there. And then how many bottles are we gonna have to taste? What's the worst case bottle we can get? Well, I think all of these, in each case, whether we jump 45, if the magic bottle is 45, right? If the magic bottle is 45, that's going to be a pretty bad case, because we're going to do one jump to get to 46. It's going to be bitter. Then we're going to have to go back to 1, and we're going to have to sample all 45 of these. Is that right? Let me think about it. So if this is bitter, then we go back and we taste. Oh no, because we already tasted 1, so we don't need to taste all 45 of these. We just need to taste the 44 of them from 2 up to 45. So we tasted number 1, then we tasted 46, and that one was bitter. And then we go back and we taste all the ones from 2 up to 45. Once we taste the 44th one, if it's tasteless, we still don't know if that's the magic potion or if 45 is the magic potion. So I think we need to taste 46 potions in that case. So we're doing 46 potions. 46 bottles, I should say. 46 bottles that we've had to taste, because we tasted number 1, then we tasted 46, and then we tasted all the ones from 2 through 45. That's in the case where this one's bitter. Now, if you go to the case where this one's bitter, this is 46 plus 44. This is the 100th bottle. If the 100th bottle is bitter, we've done 2 tastes here, and then we have to go back and taste all the ones from 47 up to 99. So let's see, what is that? 42 of those guys, right? So we've done 40. Oh, I think I added this up wrong here, because this is, oh no, that's right. There are 44 of these guys. 1 plus 1 plus 44 is 46. Here we're doing 3, because we taste 1, we taste 46, then we taste 100. So that's 3 that we've tasted by the time we get the bitter one. And then go back and we do all the ones from 47 to 49, that's another 43 more. So again, we have 46 that we've tasted in order to find out the right bottle. And then you can see it's going to be a pattern. If we jump 43, now it'll be, so we had 1 plus, or we had 2 to get to the bitter plus 44, and then in the next case we had 3 to get to the bitter plus 43, and then it'll just can keep going like that, 4 jumps plus 42 and so on. In any of these cases, you always taste 46. So I think that's the final answer, but I'm starting to think there might be one more slight optimization, which is maybe you don't have to go back to the very first bottle. So for example, do you need to taste bottle 2 if 46 is bitter? Let's say you taste bottle 1, it's fine. Then you go and you taste bottle 46 and it's bitter. Oh, actually, you know what you can do? You don't even need to taste bottle 1. You can skip right to 45, right? You can skip right to 45. Yeah, you don't need to taste bottle 1. So you skip right to 45, and that means you only have to go back and taste 1 through 44. So that's going to be 45 of them that you taste total. And then in this next, so it'll be 1 plus 44, and then 2 plus 43, and then 3 plus 42. Let me fix that. It's not very clear. Almost done here, guys. We're almost done. So in the first case, it is 1 bottle to get to the bitter one if you go straight to 45. So this is now 45. We're not doing 0. We're doing 45. We're going straight to 45. So we taste that one to get to the bitter one. Then we do 44 more from 1 up to 44. That gives us 45 total. And then we jump another 44. That gets us to 99. This is 99 now. And then we're going to have to go back. So that takes us 2 to get to the bitter plus 40 plus 42 now. Is that right? And then 3 plus 41. No. Sorry. My bad. It is 2 plus 43, and then it's 3 plus 42. These are all adding up to 45. So 45 is actually the best you can do. All right. That's the end of that problem. Sorry I got so confused on that one, but it was a tough one. And I hope you guys enjoyed this video. I'll see you guys in the next one. Take care.